thank you for the introduction. So my name is Pawan Chaurasia. I'm a lead research data scientist at Dunnhumby, and along with me are my colleagues Abhinav and Aditya. And we are presenting our work that we call as Basket Transformer, which is a novel grocery recommendation with the T5 architecture. So in retail, we usually work with two types of problems. First is reward. Reward is where we want to recommend products to the customers that they have already bought before in the past, right? And in acquisition, we are recommending products that users have never bought before. And we call these recommendations as novel item recommendations, right? So as you can see, acquisition is a much difficult problem to crack compared to reward, mainly because of two reasons. First is in reward, we are recommending products that are already that customer has already bought before, right? So we know what the affinity of that customer is with respect to that product or how they behave. But in case of acquisition, we recommend something new. So we have no idea about the relative affinity with each other, right? And second, at Dunnhumby, we work with product catalog ranging from at least 1,000K products till up to 2 million products. And customers usually buy only 4 to 500 products in a year maximum, right? So we have a huge base of products to score from, right? Which again makes it more challenging compared to reward. So unlike reward-driven recommendations, acquisition focuses on exploring uncharted customer preferences, which naturally will demand much more capable models. Right? So I just want to quickly mention the evaluation metrics that we use for such kind of problems. So this is your typical recommendation system where we are trying to predict or trying to get the probability trying to get the probability that the customer might buy a product. And then we rank order those products based on their probability scores. And precision at K and decile gain, they work really well in these scenarios. Right? So before I deep dive into what we did using the transformer architecture for this, I just want to highlight the existing approach that we are following to keep a benchmark as a baseline. So matrix factorization methods like ALS, they are typically used in the industry for such kind of a problem. Think about predicting or suggesting new movies to a user, right? New movies that they have not watched before, and these are usually recommended based on whatever the user has watched in the past or whatever other users have watched, right? So typical Netflix problem. In our case, it is something similar, but instead of movies, we are trying to predict products, right? And ALS does fairly well in these cases, right? But it has its own limitations. So first, ALS or any matrix factorization-based method, they are not designed for handling sequential patterns or to understand the context around a product, right? And in retail, the retail purchase data is sequential in nature in a way, right? So your next purchase typically is related to what your current purchase is, right? This is where transformers comes in, right? The transformer, I think we all know that they excel at capturing complex item-to-item correlations and temporal sequences within a sequential data, right? So yeah, these are the results of our ALS-based benchmarking. So precision at K, the precision at third slot is 2.26% and 1.86 and 1.49% at 10th and 20th slot, which is fairly decent for an acquisition kind of problem in retail. And ALS does a fairly good job in rank ordering as well, as evident from the decile gain. The fifth capture rate is 671%, and the rank ordering is also there, right? So now comes our approach, what we did using the T5-based, transformer-based T5 architecture. So I'm sure most of us in the room are already familiar with what T5 is. I'll just give a quick refresher. So T5 is a transformer-based model developed by Google. It treats every NLP problem as a text-to-text task, right? And they do really well in cases like summarization, language translation, or question answering. So essentially where you have a sort of input sequence and you have a target sequence as well. So now why we chose T5 for this and how does it fit in the retail scenario? So if I have to draw the analogy, then it goes something like this, right? In text, we have words and a collection of words are sentences, right? In retail, we have product IDs, and a collection of products will form a basket, right? So let's say if I go to Reliance Mart, I buy 5 products, right? So the collection of those 5 products is one basket for me in that shopping visit, right? So again, in text we have words and sentences. In retail we have products, and they form a basket, right? In text problems, we usually have an input sequence, right? So it can be, so the input sequence is usually a sentence, which is the cat sits on a mat. In our case, the input will be a sequence of baskets. So if my one basket is, let's say I bought 3 products, milk, egg, and bread. So that's my one basket that I can treat it as an input, right? And we can have multiple baskets. So basket one, then basket two, then basket three. We'll make a sequence out of it. And in T5-based problems, we also have a target sequence, right? So if it's, let's say it's a translation problem, we are trying to translate English to French, then the cat sits on a mat will translate to something like this in French. In our case, in retail, my target is whatever the customer is buying next after the input sequence, right? So if my first basket was milk, egg, and bread, then I bought jam and soda, so my target becomes jam and soda, right? So again, my input is a collection of products, which are milk and bread, and my target can be whatever basket I bought next, again, which is jam and soda, right? So, and we have seen that these text models, they usually do really well. These trained LLMs, they do really well in predicting what the next word should be, given an input set of words or sequence of words, right? So we thought if we treat our problem, the acquisition problem, in a similar way, but instead of text or words, if we replace them with product IDs and we train the model on a sequence of products or baskets, then it should give us, it should be able to predict what the next basket or next product should be, right? That's where the idea came in, right? So this analogy between text sequences and basket sequences and T5's versatility in sequence to sequence tasks made it a good candidate for this kind of a problem, right? Yeah, so now comes the technical part on how we implemented this, or how we transformed this into our retail use case. So first is tokenizer and encoding, right? So first we created a set of special tokens, token IDs from 0 to 4, right? 0 is for padding, then beginning of sequence and end of sequence as 1 and 2. Then we had a separator, special token, to separate baskets, right? Something like a full stop in English, or where we just want to separate 2 baskets. And then we get a special token to denote any empty basket, right? So the users will not buy in all the weeks, right? So wherever they did not buy anything, we'll just denote it with a special token so that the model has some extra information there, right? So these are our 5 special tokens. Then we just mapped each product ID to a unique token ID ranging from, again, 5 to n plus 5. Something like product 1 will get ID 5, product 2 will get ID 6, and so on, right? The example will make it clearer. So now we have a tokenizer encoding. The next second step is to create the input sequence, right? So for getting the input sequence, we'll take a customer's last 8 weeks of transaction data. Now this 8-week is a kind of a hyperparameter. You can use 8, you can use 16, you can use 6 months, you can use 52 weeks, 1 year, right? We chose 8 weeks for a couple of reasons. First, we are working with a very limited infra back then. So the model, the architecture was not able to handle very large sequences, right? So we had to limit it. And second reason was, the business reason was, we noticed that most of the customers, they usually buy at least once within a span of 8 weeks, right? So we were covering a lot of customer behavior within 8 weeks. But we also want, this is a retail problem and we have seasonality in this, right? So we were, so we thought just one sequence of 8 weeks does not cover the whole year's picture, right? So what we did was, we created a 52 rolling window training samples, one for each week, right? To account for seasonality. This is an example. So let's say a customer, as of any week, so let's say week 1, the customer bought 2 products, P1 and P8, then P9 and P2. They did not buy anything in 3rd week, then just 1 product in 4th week, and then there were a couple of empty purchases, so no purchases in those weeks, right? And so on. So we'll take this data, we'll do the tokenizing on it, right? We'll first add beginning of sequence, end of sequence tokens, convert all the product IDs to their respective token IDs, add the basket separator, right, which separates two baskets, add special token, add the separator, sorry, add the special token for empty baskets, right? And then we finally encode it, right? So we just convert it to numbers. This is what the model sees while training, and this is a lot similar to how text models are also trained, right? You take a bunch of text words, you convert them into numbers, and you feed it to the model, and model tries to learn the patterns, right? So this is how we did it in retail. Then with T5, we also have target sequence, right? It is pretty straightforward. So what are the customer bought in our target window in future? We'll just take a unique set of all those products, follow the same tokenizer encoding process, and then we'll get the target, right? So for example, if I'm creating my data, this data as of 1st of March, right? So my training window will be the last 8 weeks, which will be Jan and Feb, right? So I'll get this input sequence from Jan and Feb, 8 weeks. And my target window will be whole of March. So whatever I bought in those next 4 weeks, the whole of March, I'll treat those products in my target window. And these are all only the product that the customer has never bought before. And they bought it for the first time, right? Hence the novel item for training. Yeah, so we got our input sequence, output sequence, then we just pass it through a T5 architecture. We train the model. These are the training configs that we use for T5. So fairly smaller model in terms of number of parameters if you compare it with your other models, other T5 models for text, right? And then on the right, we see the cross entropy loss. So it stabilizes roughly after 20 epochs, right? I just want to quickly mention the infra that we are using, right? So back then we were working with 4 NVIDIA T4 GPUs, right? 16 GB memory each. Although these are optimized for machine learning workloads, but we were still facing a lot of constraints in terms of machine, right? Especially given the scale of data that we're working with, right? Yeah. So now we have a trained model. Now for the inference, you follow the same process for creating your input sequence. You use historical baskets as input for 8 weeks, create a sequence, pass it through a trained T5 encoder model, encoder-decoder model. And for the output, so this is a recommendation problem, right? So we are getting the output as the probabilities across all the products instead of outputting the whole sequence, right? So if we create a sequence, pass it through the model, we get the probability across all the products, and then we just simply rank order them and make our recommendations, right? Yeah. So these are the results that we got, right? And we are comparing it against our baseline ALS-based method. So T5 outperforms ALS-based method with roughly 15% improvement in precision at 10th and 20th slot, which is actually really good for retail, especially in this kind of a problem. And it outperforms ALS in rank ordering as well, as evident from decile gain, right? And the rank ordering also holds. Yeah. This is all good, but it does have its own limitations, right? So new products are launched almost every week in retail, right? And we have no information at all about their interaction with any customer in the market, right? Because they are new. So naturally they are not included in our vocabulary of products when we are training the model. So we cannot recommend for those at all. Then comes the stability issue. We work with a relatively smaller T5 architecture in terms of parameters, right? But if you want to scale it to larger data sets, or like it will demand a substantial resource. Then currently this model only works on the purchase sequences, right? We are ignoring all the external factors like seasonality, promotion, and demographics. We are not including them directly at least, right? So to tackle these problems, this is what we are trying, right? This is what we have planned as our feature improvement, right? To tackle cold start problem, we are planning on we want to incorporate a hybrid approach, right? And include product description embeddings that might help with cold start problem. The tokenizer that we are using, it's a very simple tokenizer where each product ID is mapped to one token, but we are thinking of using something smarter, right? Maybe a subword-based tokenizer on product descriptions to help better capture the semantic relationship between products. We definitely want to try a larger T5 config once we have secured better GPUs for this. And then target sequence modeling, instead of just using a set of unique products, we can also model it as a sequence, right? Just like the input sequence, and then we can train our models. Yeah, so we anticipated some questions, so I'll just walk you through them. So the dataset that we are using Dunnhumby's publicly available dataset. We call it Let's Get Sort of Real, LGSR. It is available on our website. You can download it from there, right? This it's a typical transaction dataset with roughly 5,000 products and 500K customers, so a fairly decent dataset to rest on. And this has been mentioned in many other research academic papers as well, right? Have we tested this against any other benchmarks besides ALS? Yes, we have tested this against a traditional popularity-based benchmark and a neural network-based method. ALS was the best out of these three, so we kept that as our baseline in the paper. Why T5 and not BERT or any other architecture? So we wanted to treat this as a supervised problem where we have both an input sequence and an output sequence, right? And T5 sequence to 6 model seemed a good choice for it. But we are also exploring, currently trying out BERT for like implementation for this. If this works out, we might write another paper on this, right? The infra that we're using for scaling on larger data sets, right? So as I said, currently we are using 4 T4s, right? And each training epoch would take us around 50 minutes, right? Which is huge. And the overall scoring on all the 500K customers, right, from LGS or dataset would take around roughly 2 hours. But yeah, now once we have the bigger A100 GPUs or something else, so we'll test on that, and we are trying to scale it for a bigger data set with 10 million customers, 10 million active customers. Has this been tested for different time periods? Yes. So we have tested this across different time periods of the year, and the results are fairly consistent. This is primarily because the model has seen the sequences all around there because of the 52-week rolling window, right? That's it. Here's the team. This is me. We have Aditya and we have Abhinav. Now I think we are open to questions.
Thank you, Pawan. I think questions we out of time. We can take it outside the hall if that's okay.
Sure, sure.
Thank
I'm
you.
here
Thank
the
you,
whole
Pawan.
day. You can connect with me.
Thank you, Pawan.